guys, so welcome back to another video. We're going to be doing some integration with trigonometry, and there's a lot of information in one video, so if you want to put it on 2x speed and you want to kind of have your notes with you, because it's just going to be a quick kind of like information dump. We just did it in class today, so we're going to go through this. Okay, so the first form of integration that we have is when we have an individual kind of trig function, um where it's like sine to the nx dx, right? And or it could be cos to the nx. It doesn't matter. Just one of these two. And what we're gonna do. So the first situation where n is equal to 2k plus 1, which means it's an odd number. Odd numbers are nice. You're going to see why in a second. So let's say that we're integrating, sine to the 9x dx, right? Absolutely impossible to do with like traditional methods. I have no idea how to do this unless you're taking this method, which we just learned today. So what you want to do is you got to think, okay, we want to use u substitution. And the way we use u substitution is we have to think of it in terms of, what we have to do is we have to take sine to the 8x. This is reason why odd is nice. We turn it into an even number here, and then this is just multiplied by sine to the x. How is this going to help you? What differentiates, if we do u substitution, right? We need something to equal sine x dx. What differentiates into sine x? Cos x, right? Cos x differentiates into sine x. And how do we get cos x from sine to the 8x? Well, we remember that that there is this there's this trigonometric identity, right? Sine squared x plus cos squared x equals 1. This trigonometric identity. And so what we could do is we could rearrange. We have to think, because it's an even number, it's nice because it's just something to the power of 2. Oops. Okay, it's just something to the power of 2. Like sine to the power of 2, or if we had like cos to the power of 9, for example, instead of sine to the power of 9, we'd have like cos to the power of 2. So we can manipulate it in that sense. So what I'm going to do is I'm going to rewrite. This is why odd is nice, because you get the even number after you take one out. You can rewrite this as sine to the 2x, and then whatever power makes it. So if it's to the 8, then that's sine to the, let me show you, sine to this 2x to the power of 4, right? That makes sine to the 8x, and then that's still multiplied by sine x. Okay, and now we just want something to differentiate into sine x dx to use u substitution. So we're gonna do integration of, if we rearrange this equation, sine squared x is equal to 1 minus cos squared x, right? Sine squared x. So this means this can be substituted in here. So what we're gonna do is we're gonna do 1 minus cos squared x all to the power of 4 multiplied by sine x dx. Now we're going to use u substitution, let u equals cos x, right? Because cos differentiates into sine x. So then du over dx would be equal to sine x, and du would be equal to sine x multiplied by dx. And so let's rewrite this equation with du in it. So 1 minus cos squared x to the power of 4 du. Do you see how, all of this is the same as all of this, and so we can substitute du into it. This is what we end up with. And remember, what is our u? It's equal to cos x. Therefore, we can say integration of 1 minus u cos x squared, so u squared, all to the power of 4 du. And you can just use binomial theorem to expand this to get a polynomial, and it should be simple integration. Okay, so now what happens if instead of n being 2k plus 1, which is odd, what if n is 2k, right? It's an even number. Even numbers are tough, and you're going to have to go through it like bit by bit, like decrease the power by 2 and then by 2 again, or in factors of 2. I can't really remember, but we're going to get there. And evens are harder. Just remember that. And remember the idea that when it's odd, take one out to make an even. You can use substitute, but without anything to take out, when we start off with an even, it's going to be tougher. So let's say that we have sine to the power of 4x, right? Instead of trying to take one out, what we're going to do is we're going to use double angle identities, right? Double angle identities. And the reason why we're going to do this is because of this simple thing. Cos 2 theta makes cos squared x minus sine squared x. Right away, we see that this equation is able to take you from a squared into a 1, right? And we're going to just keep on doing that to reduce the power bit by bit so that we get to just one power, and then we should be able to do it from that. And you're going to see that happen right now. So the reason why we want to use the equation because it goes from cos to the squared to cos to the zero. And yeah, so we're going to do that bit by bit. These are all theta. Let's say that. And then now there's different variations of this, starting from this one, you just do this, but then substitute it in here, and you can get different variations. So the first one is cos squared theta, sorry, minus 1, 2 cos squared theta minus 1, and then we have 1 minus 2 sine squared theta. So in this case, we have sine to the 4x, and we want to use this equation to go from to the power of 4 to the power of, like, we want to go from a higher power to a lower power. And look what we have here. We have this equation here where it has a sine squared and it goes into a cos to the power of 1. So we want to use this equation. So how do we do this? Cos 2 theta is equal to 1 minus 2 sine squared theta. And so therefore we say that let's move it all. So cos 2 theta minus 1 is equal to minus 2 sine squared theta. And then therefore sine squared theta is equal, I'm going to write it on the other side. So therefore this is all divided by minus 2. I'm going to flip the polarity. Flip the, yep, 2 theta over 2 equals sine squared theta. There we go. Now we have something that equals sine squared theta, and we can give this in terms of sine squared theta. So let's do that first. Sine to the 4 theta is just sine squared theta squared. Oh, sorry, sine squared x squared. And now, because we know that there's something that can fit, right? We can substitute this into here. So let's do that. We have now this is equal to 1 minus cos 2x over 2, right? Does that make sense, guys? And now that's all squared. So let's do this really quick. I'm going to rearrange it in a way where it makes more sense, like 1 half multiplied by 1 minus cos 2x, all of that. And then this is squared. So when we square this, it's just 1 half squared and this squared. Does that make sense? So I'm going to do that right now. The integration of 1 over 4 multiplied by 1 minus 2 cos 2x plus cos squared 2x. Okay. Does that make sense, guys? And what we're going to do here again is look here, right? We went from sine to the 4x to cos squared 2x. And we're going to have to do that jump again. We're going to have to go from 2 and go from 0. So we went from sine to the 4 to cos to the 2. And now we're going to go from 2 to something to the power of 1. We're going to have to use this again, but in this case, instead of having sine squared x, we have cos squared something. Cos squared 2x we can think of as another theta. So now we're going to use the another variation where cos 2 theta is equal to 2 cos squared theta minus 1. And so let's rearrange this to give it in terms of cos squared theta. So we have cos 2 theta plus 1, and let's just divide by 2 straight away. So that's cos squared theta. So now all we have to do is substitute it in here, just like we did before. 1 over 4, 1 minus 2 cos 2x plus, and then the whole thing that we just found, plus 2 theta. In this case, theta is 2x. So 2 times 2x is 4x. 4x plus 1 all over 2. And if you were to do this and put it out, it's all going to be like single level cos. Cos just goes, cos 2x makes sine. Actually, the integration of cos 2x is 1 over 2 sine x. 1 over 2 sine 2x. So I'm just doing it here to show the integration method. Hopefully you know how to integrate and differentiate cos, like cos ax, cos bx, that kind of stuff with the chain rule. It's quite simple. Okay. So we just finished the form where it's like f sine to the nx, right? And it could be even or odd. Let's keep going. We have so much more. Next, we have the form sine mx multiplied by cos nx. And the first scenario is either when m and or n is odd. Remember, odd is always nice. And the second case, if you look over up top here, is when the other case is when m and n is both even. And we're gonna get to that in a second. Similar methodologies. If you can remember the kind of philosophy, when you do odd, you take one out, You take one out, and then you use the derivative of something to make that and do U substitution. It's quite simple. And when we get to when both is even, you use the double angle identity. So we'll get to that in a second. You'll see how we do it. But okay, so let's say that the example I've got is that we've got sine 3x, sine to the power of 3x, multiplied by cos to the power of 3x dx. And in this case, m and n is both odd, but you can have situations where just m or just n is odd, in which case you do the same thing. So in this case, let's just take one of these guys out. So we get cos, let's take cos out. So we have cos squared x and then cos x just by itself dx. Straight away, we know that a differentiation of sine x makes minus cos x, right? And then we just have to do the minus to balance the things. We'll get to that in a second, but you can see how now we're going to have to use u equals sine x. Another thing we realize is that now cos x is in the form cos squared x. Or if this was like cos 7x, then taking that out, that would be cos, taking that out, it would be cos, gosh, let me put this back. But if this was cos 7x, we can split it into cos 6x and cos x, in which case we can just do cos to the power of 2x all to the power of 3. So it's a similar principle to how we did it before. You want it to the power of 2 so that you can transfer cos x into sine x using the thing, and then now u is sine x. So it's literally just all u's. It's just all sines, in which case u. So let's get to it. So we identified that sine x differentiates into negative cos x, and so we want to let u equal sine x because we've got sine x here. And this right here, cos squared x, is going to be able to turn into some form of sine x, right? So, and let that looks like n, u equals sine x, du over dx would be equal to minus cos x, du would be equal to minus cos x dx, and because we don't have minus cos x dx, we have cos x dx, we're going to minus to both sides, so that's minus du equals cos x dx. And now there we go. So what we're going to do now is rewrite the equation with u in it. So integration of sine cubed x cos squared x, and then cos x dx, which is right here, it gets substituted by du minus du. So the minus, let's just put it in the front because technically it's a multiplication with like -1 and then du, but I'm just going to put du here and put the minus in front just to simplify. Let me just, oh, okay. Okay, so what do we do next? We want to give everything, remember that our u is sine x, so we want to have everything in the form of sine x. So remember that cos squared x is equal to 1 minus sine squared x from the trigonometric identity. So now we have sine cubed x multiplied by 1 minus sine squared x. That's just cos squared x going to here, and du. And now all we have to do is remember that sine x equals u, and all we have to do is integration of u cubed multiplied by 1 minus u squared sine squared x, so u squared du. And if you multiply this in, that's u to the 4. If you multiply that in, that's u to the 5. So u to the 4 minus u to the 5, right? It's just a normal polynomial. You can do that pretty simply. So that's how you transform it when m and n is either one or both of them is odd. How do we do it when m and n and n are both even, right? So this is the situation where it's going to get tough. So again, we're going to have to use the two theta identities. So let's do an example. The integration of sine squared x cos squared x, right? Okay. In this case, we want to use the sine 2 theta identity, right? Because sine 2 theta is equal to 2 sine theta cos theta. 2 sine theta, sine 2 theta is equal to 2 sine theta cos theta. So let's just write this in terms of that, right? We want to write this in terms of that. So, and remember, this could be sine to the 4, right? Cos to the 4, in which case it's just another form of sine 2 theta, and we're going to get to that in a second. Or if you had like sine to the, like sine to the 4 here, sine to the 2, you're going to have to use, the cos 2 theta thing, and then you're just gonna have to transform, like let's say we had sine to the 4 cos to the 2 theta, so you want sine to be in terms of theta, in which case then we're gonna have to use to cos 2 theta is equal to 1 minus 2 sine theta. So you can see how the double angle identities, whenever there's an even, we use the double angle identities. And so in this case, let's do it with this. And we're going to use the sine 2 theta identity. And so let's say that, let's give it in the form of this first. We want this form, and then we can worry about substituting sine 2 theta. And so let's write this in terms of that. So let's give, let's say that there's 2 sine, um, sine squared x. Why did I put sine x squared? Sine squared x, and cos squared x, right? So 2, how do I describe this? Sine 2 theta equals 2 sine theta cos theta. Now, to be able to have sine squared theta, cos squared theta, technically you'll have to square everything, right? So for example, like I'll square both sides. What's this gonna turn into? Sine squared 2 theta is equal to what's it called? Sine squared 2 theta is equal to, that's an I. Sine squared 2 theta is equal to 4 sine squared theta cos squared theta, right? And this is more similar to what we have. Instead of theta, we have x, but it's the same thing. So what we can say is we need to give this form, right? 4 sine squared theta, sine squared x, sorry. 4 sine squared x cos squared x. And initially we didn't have any coefficients, right? It was 1 multiplied by the whole thing. So we need to find a way to balance out the 1. That would be here. 1 over 4 times by 4 would be able to equal to 1. So this form is completely equal to the form up here. Same thing. It's just we're describing it in a way where we can substitute sine squared 2 theta in. So now we have this, and this is just equal to this, is equal to this, which is just equal to sine squared 2 theta. So now we can say the integration here is equal to 1 over 4 sine squared 2x, right? So what we've just done is we've gone from a complicated one where we can't take anything out. Remember, both of them are even, so we can't do the taking thing out with the odd. So what we've done is we've gone from sine 2x to cos multiplied by a cos 2x, and we've gone from that to 1 over 4 sine squared 2x. So now all we have to do is use the cos 2 theta identity. In this case, we want to turn a squared into a non-squared, right? So let's say that's this one. So see how we want to turn squared into no squared. So just do this. So 2 sine squared theta, that looks like 2 sine 2 theta, so I'm going to do this to make it more obvious. So now we're going to do that. So let's give it in terms of sine squared theta. I'm going to do it really quick because I did it before. 1 minus cos 2 theta over 2. Let me just check. 1 is 1. Then the opposite. Okay, perfect. So now we can substitute, right? We have sine squared 2x, sine squared 2x, whatever, right? Sine squared 2x, 2x is just like y, or we can think of it as theta. So we have sine squared something. So then we can say, we can substitute this into sine squared 2x. So we have integration of 1/4, and then instead of sine squared 2x, we have whatever we found. So we have 1 minus cos and 2x, right? This is 2 theta, so we need to multiply by 2. So 2x multiplied by 2 is 4x cos 4x over 2. And then this is the equation, and all you have to do is integrate this, and you'll be able to find the answer. So yeah, that's how you do it when it's even. Remember, odd is when you take one out and use substitution. Even is when you use the double angle identities to repeatedly remove the powers. That's how you do it. Okay. Next form, what we have is we've just finished sine nx, cos nx. We're gonna go to the form where it's like sine A cos B, or like sine A sine B, right? All these different forms. You'll understand with an example. And to do that, we're gonna have to use these equations here. Look down at the bottom here, where my mouse is. That's where the magic happens. So these top 3 equations here are derivated from the compound angle identities at the bottom. I'm just going to go straight up and memorize these because I am not going to be able to derivate these like from this to this. So I'm going to try to remember these, but we're going to use this equation and it's going to be quite quick. So let's give the example where it's integration of sine, for example, 5x and cos 4x dx. Okay, how are we going to do this? Well, we're going to look for a form that looks similar. We have sine A cos B. That's the first form, right? Because the second form is sine A sine B. Third form is cos A cos B. Here we have one sine, one cos. So it's the first form, sine A cos B. So we now have to give it in the form. I'm going to rewrite the whole equation here, where it's like 2 sine A cos B equals to sine A minus B plus sine A plus B. Okay, so we're gonna have to give sine 5x cos 4x in the form of 2 sine A cos B. How are we gonna do this? Well, let's rewrite. Let's just say we do that. 2 sine 5, we need a 2 there because that's how the equation works. So 2 sine 5x cos 4x. So that's the equation that we want to work on. But this is 2 times larger, right? Because this is 1 sine 5x cos 4x, and this is 2 sine 5x cos 4x. So what we need to have is 1/2 here. 1/2 cancels with 2. That gives us the original equation. So now we've just written the original equation in the form of the new form that we want to add in the substitution of the equation that we have. And so what we're going to do now is we're going to substitute this whole end into here. And so what this equation is going to turn into is the integration of 1/2 of and now we have sine, what's A? Sine A is 5, so sine 5x minus 4x, because that's cos B, and then plus sine, and then them both together. So 5x plus 4x. Perfect. And once you do this, integration of 1/2 sine, so this is just sine x plus sine 9x. And all you have to do is, again, integrate with chain rule if it's 9x. If it's just x, then you don't have to worry about that. But yes, so that's it. That's actually quite a simple part where it's like sine A, sine B, sine A cos B, cos A cos B, that kind of stuff. Remember these equations. I'm going to try to remember them. Okay, last form is when we have integration of tan to the mx multiplied by sec to the nx dx. And there's going to be 2 situations again and we're going to look at this in terms of m and n, and there might be like some gaps in terms of like which situation is covered, which situation is not. So let's say the n is odd, right? N is odd is great again because we're going to do the same thing as all the other odd sections. We're going to take one version of sec x out, and the reason why we do that is the differentiation of tan x is equal to sec x. Let me just check if that's true. Differentiation of tan x is equal to, nope, and is odd. Take sec squared x out. Tan x equals sec squared x. Okay. Yes, the differentiation of tan is that it's tan x. Differentiation of tan is sec squared x. I'm gonna pause really quick, check something. I'll be back in a okay, so I'm back, and I don't think this is for n equals odd. I copied this from my teacher's notes, but I think it's n equals even. It seems to only work if n equals even. Um, I will make a correction video if it happens to not be n equals even, but I think it's n equals even because we're not taking out 1 sec x, we're taking out sec squared x. So yeah, but let's get back to this. So tan to the mx multiplied by sec to the nx dx, and n is even. So we know that the differentiation of tan x is equal to sec squared x. So this is actually similar to the odd when it was odd, because we're taking something of sec x out, and then tan x differentiates into that something. In this case, instead of it being like cos x differentiates into sin x, which then it's a 1 exponent, so you only take 1 out. That's why odd is preferred. But in this case, sec x, we take sec squared out because tan x differentiates into sec squared. So actually, this function's really like the odd function. So let's go for it. So we want to take, I'm not going to have any examples because we didn't do any examples in class, but let's just take so we want to take sec squared out because tan x differentiates sec squared. So we do sec n minus 2 x, and then we have a sec squared x right here. Okay, and since tan differentiates into sec squared x, we're going to let u equals tan x. du equals sec squared x, du dx, and then du itself is equal to sec squared x multiplied by dx. This section here exists right here, right? Same thing, so we can substitute du into this. So let's do that. So we have tan to the mx multiplied by sec to the minus n to the minus 2x, and then we have du. Okay, now we have to write everything in terms of tan x, because remember u equals tan x, so we want everything to be tan x. So let's rewrite this equation, but I'm gonna write down the identity first. So we have a few trigonometric tan identities as well. So we have 1 plus tan squared x equals sec squared x, and we have 1 plus cotangent squared x equals to cosecant squared x. So the way I remember this is tan, let's start with 1 plus cotangent squared makes cosecant squared. Meanwhile, the non-co ones, 1 plus normal tan x squared equals normal sec x squared. So that's how it works. Not sec x squared, sec squared x. Okay, so that's what we're going to do. I should have kept that in. So 1 plus tan squared x equals sec squared x. And we want to move sec into tan, right? We want to turn sec into tan. So we're going to rewrite this equation, sec squared x. Actually, that's already, it's just in the other way. Okay, perfect. So, and now we're going to do this. So remember that n was even, right? It was an even number. So let's say it was like sec 10x, sec 10x, right? We took 2 out, so that turns into sec 8x and sec squared. And sec squared is just turned into like du. But sec 8x we can rewrite as some factor of sec squared. Check this out. Sec squared, we want it in sec squared. So sec squared and then sec, if this was 8, sec squared x to the power of 4. Right? So the whole magic of it being even is that we can do it in terms of that. So n minus 2, and then we can just do, let's rewrite 10x. Oh, my pen's not working. Okay. 10x, tan to the mx, and then sec, we can do sec squared x to the power of like whatever the thing is, n minus 2 over 2, in which case it's like 10 minus 2 equals 8, 8 over 2 equals 4, which is what we've just done there. So when it's in this form, yeah, and then dx, and oh sorry, this is du, and now we just remember u equals 10x, so we're just going to put actually no, not yet. Sorry guys, and now we're gonna turn sec squared x into whatever this is, 1 plus tan squared x. So now it's equal to 1 plus tan squared x, all to the power of n minus 2 over 2. And this, and now remember that tan x equals u, so now all we have to do is say u to the power of m multiplied by 1 plus u to the power of 2 multiplied by all to the power of n minus 2 over 2 du. And this is quite simple. This looks complicated, but if you just imagine all of this equals 4 as our example before, it's just binomial and then multiply it in. It's going to turn out to a polynomial, super simple to do. Okay. Now, if in this case we had tan, let's rewrite the equation, tan to the mx multiplied by sec to the nx dx. In this case, we'd say that, so we just did n is squared. Now let's say that m is even, right? Because in this case we can take, actually no, I'm gonna pause really quick. Sorry. Okay, so I just checked, and in this case m is odd, right? So we've had a situation where sec to the power of n, where n is even, because we want to take sec squared out, right? But in the case where m is odd, what we're going to do is we're going to take one tan out, right? Tan to the 1 out, and then we have tan to the some even power, we can turn it to tan squared to some power, right? So when m is odd, we want to take one tan out. And the hint to this is that the differentiation of sec x is equal to tan x sec x. It takes one of each, right? Tan x sec x. And so in this case, we'd want u to be equal to sec x. And then it doesn't matter what power sec is, because it's just be u to the whatever power. So if it's odd and we take one sec out at like 9, sec 9, and we take one sec out, then it'll be like sec to the 8. It's just u to the 8. Doesn't matter if it's u to the 8, u to the 7, it's all the same. So in this case, m is odd. What does this mean? We take tan to the 1 out, because then we have tan to the 1x out, write that one, tan to the 1x out, because then we want to have tan squared or some factor of tan squared so that we can turn it into sec x. So let's do that. So we have, so if we know that d of dx, differentiation of sec x, is equal to tan x sec x dx. Yeah, no, tan x sec x. Then we want to take one sec x and one tan x out. Does that make sense? So we have tan minus 1x and sec to the n minus 1x. Minus 1x. There we go. And then now we have a tan x and a sec x just waiting out here next to this dx to be substituted. Next, we take let u equals sec x. So du over dx, gosh, du over dx equals 10x sec x du equals 10x sec x dx. And now this one exists right here, right? They're the same thing, so we can substitute du into that. So we have tan to the m minus 1x sec, say n minus 1x multiplied by du. And now, remember that tan x was once a odd number. So if tan x was like tan to the 9x, right? Then we just took one tan out. So that would be now tan to the 8x. So we can do something to the factor of 2. And let's just recall that the identity of 1 plus tan squared x equals sec squared x. So we want stuff in sec squared x. And tan is some even number right now. So we can just take tan squared x, and let's rearrange this for tan squared x really quick. Tan squared x equals sec squared x minus 1. So now we want we want stuff in terms of tan x so that we can substitute sec squared x minus 1 into it. So what we're going to do is tan squared x, and then this is just to the power of m minus 1 over 2. Does that make sense? Same thing that we did before. And let's just give an example. If it's tan 9x at the start, we take one tan out. So we have tan 8x and tan x, and then this tan x was used for du, and so now we have this tan 8x. We just do tan squared x to the power of 4. So we just took 9 minus 1, which is 8, 8 divided by 2, which is 4, which is we end up here. So that's how this works. It just looks a bit complicated. And now we have sec, and we still just have sec n because we took one sec out, so we have sec n to the minus 1x du. Okay, and now we just substitute. See how we have tan squared here and we have tan squared here. We substitute that into tan squared. So that gives us the integration of sec squared x minus 1 all to the power of m minus 1 over 2 sec n minus 1 du. And then now we just remember that u equals sec x. So then we have the integration of u squared minus 1 all to the power of m minus 1 over 2. Remember, it's not crazy. It's just like 4. Let's say it's equal to 4. So it's just simple binomial theorem. And this is just u to the power of n minus 1. So n minus 1 could be 9 minus 1 could be 8. So it's all polynomials. You can do this really easily with integration. So yeah, that's it, guys. So thank you for the time. I've recorded this twice now because I failed my first recording. But thank you guys for watching. That was a long video, but hopefully that adds as like a better way to kind of revise this topic, because I'm going to go and memorize all these things and watch back. So thank you guys. Thanks for watching. I'll see you next time.